So, hi everyone, we're the Bald Badgers, and our project for data science was the AI predict GDP per capita for the country. And what our project does is that our team has created a program that employs a machine learning to predict the GDP of country, utilizing certain socioeconomic metrics of the country provided by the user. And why we made it, we decided to create this project as we wanted to learn about the fundamentals of machine learning and identify the factors which play an important role in influencing GDP per capita. And this project could potentially aid others with decision-making and socioeconomic aspects. And we use a data set which includes averaged values for aspects like net migration, GDP per capita, death rate, birth rate for every country from 1970 to 2017. And our data set includes some of the aspects like arable percent, crop percent, agriculture, industry, and service. And some of the metrics for countries are null, so we fill these values with median metric value of the region the country is in.
Okay, so here are some visuals that helped us analyze our data. So first up, we have a heat map which shows the correlations between our top 10 most impactful features according to our random forest model and our target variable, which was GDP per capita. So as we can see in the scale to the right, yellow means that there's a strong positive correlation between the two variables, and dark purple/blue is like a strong negative correlation. So some interesting observations that we can make are that phones per 1,000 people and GDP per capita have a strong positive correlation, and then birth rate and GDP per capita have a strong negative correlation. So next up, we have some scatter plots. So this is a scatter plot between GDP per capita and infant mortality. So as we can see that the relationship between these two variables is logarithmic. And this is a scatter plot of phones per 1,000 people versus GDP per capita. So again, we can see that the relationship between the two variables is more logarithmic than linear. We also have a 3D scatter plot between literacy percentage, GDP per capita, and phones per 1,000 people. So again, like all our data is pretty logarithmic. And this is a scatter matrix of our different variables. And so we can see like most of them have logarithmic relationships or like no correlation at all.
During our exploratory data phase, when we're just looking at the data, we researched 3 or 4 different models. The first one being decision trees. And now decision trees are pretty useful. You can use them for either classifying or predicting data. Classification would be something like classifying images as you would do in computer vision. Regression would be something like predicting future data, which is what we're doing. Basically how a decision tree works is that it creates a tree-like structure by dividing data based on important features, and that forms decision and leaf nodes. The algorithm keeps on splitting up this data until it reaches a stopping point. This algorithm is pretty easy to understand, and it can handle many different types of data. Next, we have the random forest, which is an ensemble type model. This basically means it combines a bunch of different model outputs into one larger output. This makes the model more resilient to noise and a better overall prediction. Next up, we have stochastic gradient descent, or SGD. This is a bit different than the other machine learning models that we're using, mainly because this is an optimization algorithm for other machine learning algorithms. What's unique about stochastic gradient descent is that it processes data in batches, which is why sometimes you'll see neural networks have a batch size parameter. They introduce some randomness and noise into the data to provide some resilience to the algorithm. Lastly, we research multi-layered perceptron neural networks, or just neural networks. This is a type of machine learning model that's made up of many nodes and layers. Each node has a weight associated to it that determines the activation function parameters and the threshold. An activation function, such as the ReLU function, takes an input and based on that gives an output, which is above or below the activation threshold. And this causes the node to be activated or disabled. Each layer has a number of nodes, with all the nodes feeding into the input of the next layer for this particular neural network model type, called a feed-forward neural network. And finally, from all those different interactions of the nodes, an output is generated. In this case, it is predicting a future value.
So there were some limitations for some of the models. Some models, such as the multi-layer perceptron neural network, overfit to the training data and had poor validation scores. And the overfitting was likely due to the small data set size that we used, even though some of the models managed to handle this data really well. Most of the sklearn models performed very well due to a combination of hyperparameter tuning, feature engineering, and data scaling. The neural network, our only model using PyTorch instead of sklearn, was not highly tuned due to time limitations. The size of our dataset is an obvious limitation. However, our accuracy was high for most of the models, and time was a limiting factor as well, specifically limiting how long we could spend tuning our neural network. Another challenge was trying to find the most important features in the dataset, as there were a lot of features that improved the model's performance, but were obscure and not usable if the model was deployed for public use.
So how do we actually determine how well a model does? Well, in data science, there's two main methods, such as R-squared and mean absolute error. Now, R-squared is a measure of how well data fits a regression model, like basically just how good it fits the graph. And the value of R-squared can range from 0 to 1, where 0 means our model does not predict any variability, and 1 means our model perfectly fits / predicts our data. Now, it can go negative, but that's when things go really, really wrong. So for them, we have MEE, mean absolute error, and it's a way of testing how accurate your model is. It's a lot more intuitive than R-squared, but unlike R-squared, the values you get from mean absolute error can vary from dataset to dataset. In our case with GDP per capita, an MAE score of 100 would be amazing. But if we try to predict resting heart rates, 100 would just be horrible. Now, and our mean squared error represents on average how much predicted value differs from real value. Now, for each model, we use a Boolean plot to show the distribution of our predicted GDP and the actual GDP in our testing data. And we overlay both of them to show the differences. Now, our best performing model was the decision tree with a final R-squared value of 0.8 and MEE of 2,865. We mainly improved this through hyperparameter tuning and feature engineering. Now, we use sklearn's grid search function, and we found the one of the most consistent parameters that we should use for criterion was Freeman MSE. Now, we did some feature engineering, and we decided to select the top 12 features, which included phones per 1,000, net migration, and infant mortality. Here is a Boolean graph showing the distribution of the predicted GDP per capita and actual GDP per capita of 227 different countries, where blue is actual GDP and red is predicted. Now, our second best performing model was random forest with an R-squared value of 0.77 and mean absolute error of 2,885. Similar to decision trees, we improved this through hyperparameter tuning and feature engineering. Again, we use grid search, and we just use it to find best parameters for criteria, max depth, etc. Then we selected top 15 features for feature engineering, and here's our graph again. Now, next is stochastic gradient descent. It's a third best performing model with an R-squared value of 0.7 and mean absolute error of 3,653. Now, unlike the other models, hyperparameter tuning didn't improve it at all, because this results resulting in us using default parameters. But when you did some feature engineering and scaled your data, it significantly improved your model. Then lastly, we have our MLP neural network. This had an abysmal R-squared value of -1. And so that means there's absolutely no correlation in any slight way to our actual data, and had mean absolute error of 10,000. It's a nice number, but it's really big.
So as stated earlier, time is a limiting factor for us, and more time would have allowed us to specifically improve our neural network. Our neural network could benefit from experimentation with model architecture, such as trying different numbers of hidden layers and hidden neurons. The PyTorch library also provides a number of optimizer and loss functions that we barely even looked at. With more time, another expansion that could improve the performance of our models is expanding our dataset. Our original dataset is quite small, representing the averages of GDP and predicting features for 227 countries over the course of several decades. Instead, we could look at the sources of our dataset and pull data annually. However, this scraping process could be relatively labor-intensive and time-consuming. Another expansion could involve more scaling. Our data really benefited from scaling, though we mostly use scaling to normalize our features to have the same range. Many of our features seem to be logarithmically or polynomially related to GDP, and scaling these relationships to be linear can often improve model performance.
Okay, so here we have our interactive page. So we allow a user to input values for the top 15 features according to our random forest model. So for each of the input fields, there might be some limitations, like for phones per 1,000 people, we've limited it so that it can't enter a number greater than 1,000. And then for agriculture, industry, and service, if you recall from our data set page, it's a value between 0 and 1 because it represents the percentage of GDP that comes from that sector. And then for arable and crops, it's like the percentage of land that can be used to grow crops and are actually used to grow crops. So it's a value between 0 and 100. And then as we can see, this is our output.
Oh, and we can just try to let's try to say 1,000.
Yeah.
Yeah.
So I'm Advait, and I'm 16-year-old junior from New Jersey, and I helped in this project, and I like to swim, play tennis, read, and play ping pong. And my passion for programming started in middle school and has been able to grow due to this AI camp.
Hi, my name is Andria, and I'm a 16-year-old senior living in Pennsylvania. So I love reading books, coding, and playing table tennis. And my interest in computer science began since 8th grade, and it was when I was first introduced to coding. And since then, I improved my knowledge in the computer aided area, and I accomplished quite a decent amount in that area. And AI Camp has given me the chance to learn about machine learning and deepen my knowledge.
Yeah, hi, I'm Autumn, and I just graduated high school, and this fall I'll be majoring in information systems at CMU. And in my free time, I like to do puzzles such as crosswords and sudokus.
Hi, I'm James. I'm really regretting writing this in third person. So I'm from Canada. I love all things science. The main reason I joined this camp is so I could get tools to do more research, And in my free time, I like to read things and bake.
So I'm Krish. I'm a 16-year-old high school student from New Jersey. I love hiking, cycling, photography, and programming. My main interest in doing this AI camp was to learn about data science mainly. I go to a FRC robotics team, and we produce a lot of data on our robot, match data, data about the performance of the robot. And I really wanted to see how I could leverage some data science to maybe make the team better.